Hi there, Daniel, and again I'll be teaching physics today. So I'll be showing you how to deal with simple AC circuits. What is an AC circuit? AC means alternating current. So now, usually these circuits, let me just give you example of such circuits. These circuits usually contain three major components. Okay. Number one is the resistor. Number two is the capacitor. And number three is the inductor. So these three things are usually contained. And they are usually connected in series. Don't forget, they are usually connected in series in a simple AC circuit. So but this is not really what makes them AC or not. What makes them AC circuits is the fact that they are connected to an AC source. So I'll connect this to an AC source. So this then is an AC circuit. So you know that unlike DC circuits where you can have resistors, for instance, something like this, and these connected together, and it will be connected to a cell or a battery. This is a DC circuit, and because this is a DC source, you get. But this is an AC source. AC means alternating current. So according to the name, it's very easy to define what an AC is, because you'll have just alternating current. So what is an AC? Or permit me to shift this. So what is an alternating current? Okay, so an AC or an alternating current is that current that changes its value, right, sinusoidally and periodically. It does so in such a way so as to reverse its direction as well. So that means as it changes its values, it's also changing its direction. Okay, so that's basically what an AC is. Alright, so this class is not so much of the definition, but so much of the calculations to get the mathematics right, because basically what gives students problem most in this topic is actually the mathematics. They just look at the formula and say, oh god, these formulas are too much. How do they expect me to know all this in my head? I mean, how can I, yeah, I understand, because the way and most of the textbooks you have to consult, they really don't, they didn't even help the matter. They just, poured out all the formulas, and we are there just trying to cram everything, and it's just looking too much. So yes, this class is just for you not to cram any formula at all, just for you to know how to solve questions on AC circuits without you cramming formulas. So I won't be doing much of proofs, actually, just little things. So now, but it is important to know that the fact that it is sinusoidal means that it follows a sine function. Alright, so I'll draw the sine function. This. Okay, so, and don't mind my diagram. This is smaller than this, but then in the real sense, it's supposed to be equal. So, this is sinusoidal. So this actually shows us that this graph this function is sinusoidal. So yeah, we have T, and then here we have either voltage or current. But I would actually like to talk about current more. So although any of the two works, okay. So now at this place, this is the peak. Just if I trace it to this is the highest value that you can have, right, for this voltage or current. Also on this side too, I can trace it. This is the highest, this is the highest positive value, right? This is the highest negative value, okay? So that you can have for this current, or this voltage. So this is the peak. Okay, so we call it peak voltage, or you say peak current. Okay, so and let's say this. Okay, let's say we are trying to watch the motion of an electron in a conducting wire. So let's say it's an electron that is moving. Okay, and then go to this, let's say this junction, where we just, so we can look at that, and so from this to the source, okay, we draw this, and then we have the angle theta. So this line that I've drawn becomes the peak voltage or the peak current. Okay, so now so this is the line for the voltage and the current, so I can replicate it and then bring it here. Okay, and also call it the peak voltage. Okay, so if that's a peak voltage, I can call it the voltage or the current. Okay, because they are parallel lines, so I can reproduce them. So something like that. So form this kind of triangle. Okay, so I can draw the triangle. So you have something like this, you have something like this. Okay, and then you have something like this. Don't mind my diagram. Okay, so this is theta, this is V. Okay, don't let me use V, let me just use I. Let me use current. Okay, this is I, and then this is I naught. Okay, and then this is T. So this makes sense. I can look at it for the relationship between I and I naught. Okay, how will I do that? It's very simple. I think I'll use sine theta, alright, equals to opposite over hypotenuse. Okay, so that will be I over I naught. Okay, so this will imply that I equals to I naught sine theta. Okay, so this makes sense. But then I've not really gotten the sinusoidal function just yet, although I've actually done something quite reasonable. Okay, this still looks like sine theta. Where's theta coming from? Okay, this is theta here. But then looking at the graph that we sketched, this is a curve of, or a graph of V or I against T. So T is not showing here yet. We have to make this a function of I and T or a function of V and T. So that's what we are going to do. We want to express this as a function of T, this I to be a function of T, or if we are using V, V2 will be a function of T, not a function of theta. So how can we do that? So we need to look for a relationship between theta and T. So that will bring us back to this cycle again. Okay, so because this is a complete cycle, obviously. So a complete cycle. So now this is half of a cycle. Okay, this is also half of another cycle. You see, they look like semicircle, isn't it? There's actually a mathematical exegesis behind this, but then to save the whole time, okay, but it's just that a cycle is equal to a circle. Alright, so that means this complete cycle, I can represent it as a circle, something like this. It's just like you looking at it and then flipping the one that is under, this semicircle under, flipping it over. You know, you are going to have a circle actually. And then with this line in place, okay, and this is the center, so this is the electron that we're talking about, and then we have this, and this is theta, and then don't forget we have the vertical line, okay, the vertical line which we reproduced to this junction. Okay, reduce the vertical line to this junction. Okay, and so that is not so much of an issue. The vertical line is not really necessary now. Okay, so because we want to look at the relationship between the time t. Alright, so this is t here, this is time t. Okay, and this is v and then v. So now you want to agree with me that linear velocity v. Okay, let me use this type of v for velocity so that you don't confuse it with voltage. So linear velocity v is distance over time, isn't it? So now you agree that angular velocity omega will be angle turned through per time, isn't it? Okay, so for look at this now, because it is angular, this is angular. Alright, so we are talking about angle. So looking at this electron moves from here, let's say it moves from here to this equilibrium position. So it has turned through a particular angle theta. So the velocity of that electron from this junction A to this junction B, we call it omega, angular velocity. It's the angle that you have turned through per time. Okay, so and then I can say that my theta ends is omega t. So we have that, and then don't forget that okay, what if, so we have two cases actually. What if I'm dealing with a whole complete cycle, so that means that if I'm dealing with a whole complete cycle, alright, so I'll do this omega, let me call it omega c, this omega complete cycle. So my it's still theta over t actually, but then my theta is now a complete circle, which is 2 pi, and my t here is no longer just ordinary t, but then it is now the time taken to complete a complete cycle. What is the time taken to complete a complete cycle? We know that that is the period. Okay, so then we have that the omega, okay, is 2 pi times 1 over big T, and then this is 2 pi f. Alright, so I can come here and then change this omega to 2 pi f. So we have that theta is omega t, then this omega is now 2 pi f t. So now my theta is 2 pi f t. So having gotten theta in terms of t now, I can now bring this and put it into this my equation that I have here, that I equals to I naught sine theta. Okay, because we said that we wanted to express I as a function of t. Okay, so then we already have t, theta as a function of t, so we just substitute. So now I'll then put this, let's call this equation asterisk. We call this one equation asterisk. So we put equation asterisk into asterisk, right? Put asterisk into asterisk, isn't it? So we are going to have that I equals to I naught sine 2 pi f t. So this will conveniently represent this function, this graph that we have up here, this sinusoidal wave function, this graph. It will conveniently represent it now, because we now have I as a function of t. Okay, so now it is a ground rule for you to know that I now is I naught sine what? 2 pi f t. If it is also V you are talking about voltage, that will be V equals to V naught sine 2 pi f t. No biggie, right? Quite simple. So now this I here actually is the I can say that it is the effective current, okay, effective current, okay, and this I naught, okay, is the peak current. This is the peak current, okay. So now conditions are and all how that this can actually lead us to the RMS value. Okay, so what is RMS value? RMS value is the root mean square value. Okay, so this is root mean square. That's what RMS means. So we have the root mean square for voltage and for current. So they call it IRMS and then VRMS. So we want to talk about that. So if I equals to I naught sine 2 pi ft, okay, let's go back to that theta stuff again. Let's take all these to be theta. Okay, so that means I equals to I naught sine theta. So that you know that theta, what if theta is pi over 2? Okay, pi over 2 is like 45, right? And then what is sine 45? Sine 45 is 1 over root 2. Okay, so then this will be I equals to I naught over root 2 when theta is 45 degrees, isn't it? Okay, so this actually is the RMS value. Okay, mathematically we have that IRMS, okay, is I naught over root 2. It's as simple as that. So I naught is IRMS is I naught over root 2, and if it is also VRMS you are looking at, VRMS will be V naught over root 2. As simple as that. So you need to note that. So we can actually express these the root 2. I think this is 1 over 1.414. Okay, high note, and I think 1 over 1.414 should be 0.7071 I naught. Okay, so also for V naught, it will also be 0.7071 V naught. Okay, you can actually confirm that figure, but it should be correct. So now, as I said, it's just for you to get the major concepts. So that's IRMS and then VRMS. So the root mean square value, you can check the definition of, is actually the it is the effective, let me say current now. It is the effective current, okay, the effective AC current actually that will provide the same heating effect, as what as a corresponding DC. So it's as though when we are talking about RMS, we are talking about the, not really that is you are converting AC to DC, no, but in the real sense you are saying that, okay, the peak voltage. Okay, so now let me quickly show you something picturesque. This is an AC source. Okay, so from this source, alright, alternating current is coming out, and then so it is passing through, let's say, this resistor for instance, and then it is going. So now you agree with me that what RMS believes is that not all the currents that is coming from this mains, all right, from this source, let me call it mains, not all the current that is coming from this source or this mains is reaching this resistor box. In that, because in that, not there are some currents that have been wasted along the line. So only a few currents get to reach this place, which is the effective current. Okay, so what RMS is saying is that, okay, let's say by applying this peak voltage peak current to this resistor, I have heating effect H0, okay, and then I take this resistor and then I apply a DC to it. Now, not an AC, I apply a DC to it, and then I also obtain H0. It's saying that the value of the current of this DC current that gave me this H0, alright, that gave me this same exact heating effect is the same thing as the RMS value that yield this H0, but it is not. So what it is saying is that this I0 is not what gave rise to this H0. Ideally, I0 will give rise to something more than H0. Do you get that now? Because the current is much, but what happened is that along the line, some of the current has lost. You get that now? Has been wasted. Then we have a few current reaching this guy, producing an heating effect H0. So for me to know the amount of the current that is reaching this resistor that is producing this heating effect H0, I can just measure this heat that is being produced and then look for a direct current that will produce the same H0. The value of this direct current that will produce this H0 is equal to the value of the currents coming from this mains, alright, that produce this H0, which is the RMS value. So that means out of the current, so I can, let me make it more picturesque. Let's say this is all the currents coming from these mains. Let's say there are 3, okay, coming from the mains, okay, and before getting to the guy that they are going to meet, it's saying that some is lost along the way. Let's say this guy is lost, and then so only 2 is reaching this guy. So the 2 that is reaching this guy produce an heating effect, let's say H2, because there are 2, produce an heating effect H2. So this that is producing an heating effect H2 is the IRMS, while this that is coming from the mains is the what? I0, the peak voltage. So along the line, some guys are lost. So, but these 2 guys were able to reach this to produce the heat H2. So now, what RMS value is now telling us is that, okay, for me to know the value of this current, okay, because okay, I know the value of my current that's coming from here, quite alright, but I don't know the value of the current that is producing this heating effect that actually eventually got to this place. I don't need to stress myself with the current. All I need to do is to get this heating, okay, let's say this heating effect H2, get a DC, apply it to the same resistor of the same value. Okay, let's say this resistor is like R1. This one too must be R1. So I'll apply some DC currents to this, alright, to this R1, such that it will produce H2 for me. So this DC current that is producing, DC current does not reduce, you get. So this DC current that is producing this H2 is the same thing as this RMS current here. So inadvertently, we can say that we are looking at RMS value from the lens of a DC, although it is not equal to the DC, you get. But then we can say we are looking at it from, because this will actually help us to understand when we get to voltage, the V equals to IR, V equals to IXL, IXL, and all those things. We are going to, because this RMS value is actually what makes us to be able to bring in what's it called now, Ohm's law, okay, into into AC. So we are going to look at how all these things actually work hand in hand. So basically, that is what RMS value is. So now we have that, don't forget that VRMS or let's say IRMS. Okay, no, let me write this one after the other because it can be confusing that way. VRMS will now be V naught over root 2 or 0.7071 V naught. Okay, and then IRMS is I naught over root 2, okay, which is 0.7071 I naught. So now something interesting here. This formula shows us how that if the current that is entering, that is coming from the mains, okay, if the current is 100 amperes, it's saying that the current that will eventually reach this load or this resistor is 70% of the current coming from the mains. So that means if my peak voltage coming from the mains is 100 amperes, it shows me that just 70 amperes we have heating effect in this resistor. Do you get that now? So that means 30% must have been wasted along the line. Do you understand? So the peak current is much, but then by the time before it gets to this guy, only 70% will produce a heating effect. Only 70% will produce a heating effect, because this is like 0. Okay, let's say 70.1% actually. Approximately 70.7%, approximately 70 or less 71% actually. Only 71%. Okay, let me say 71% will produce a heating effect. Do you get that now? So that is so we can actually see the RMS as the effective current or the effective voltage that will actually produce that heating effect. You get that now? Because not all the 100 that is coming from these mains will produce an heating effect. Only 70%, 71% of it will produce the heating effect. I think that's clear enough. Okay, so that said, now we want to look at. So I said something earlier on while I started that there are major three components that we can see in AC. Okay, we have the resistor. This is the resistor. Okay, we have the capacitor, and then we have the inductor. So inductor is like a coil. So these three guys are usually connected in what? In series. But then note that, you know, this circuit does not always contain all those three. Okay, it can either contain the three. So now there are basically different types of circuits you can have. You can have an RC circuit, you can have an RL circuit, and you can have an RLC circuit. So now this is a resistor capacitor circuit, a resistor inductor circuit, a resistor inductor. You can also have an LC circuit, an inductor capacitor circuit connected together in series. You get? So these are the four types of circuits, because basically they are just three. So this is the way I can combine them. All right. So this is the four ways you can have, four ways of arranging, because the arrangement actually doesn't matter. If R comes before C or C before R, it's still the same thing. So this is RC, RL, RLC, and LC. So these are the four major combinations that you can have. Okay, now so this is a resistor R, this is capacitor, and this is an inductor. So now let us talk about, so before we go ahead now, I need to talk about reactance. Okay, so let me quickly explain reactance. So now reactance is like internal resistance offered to the opposition of flow of current by each component, you know, of an electrical circuit. So for instance, now a capacitor has its own reactance. So because a capacitor is made up of you know, some components, metals, and all, so it will have its own internal resistance to the opposition to flow of them. So, but it is not called resistance; it is called reactance. You know, a resistor basically offers resistance. That's what it does. A capacitor is not there to offer resistance. A capacitor is there, you know, just to store charges. All right, but in doing that, it is made up of some components like, you know, some metals and all that has internal resistance in them. So you have to put those resistance into consideration. So that resistance is what we call the reactance. You get that? So we have, so for that capacitor, see, it is called the capacitive reactance. And for the inductor L, it is called the inductive reactance. Okay, and so this is represented as XC, represented as XL, and mathematically we have that XC is 1 over 2 pi FC. Okay, you know that 2 pi F is omega, don't forget it. So we can say that this is also 1 over omega C, and the XL is 2 pi FL. So we can say that this is omega L. Okay, so now pay attention. Where F obviously is frequency, okay, frequency of the electrical source, okay, measured in hertz. Okay, where XC, we already know what XC is now, capacitive reactance. Okay, it is measured in ohms because it is resistance, and then C itself is the capacitance of the capacitor. The capacitance of the capacitor. So, and capacitance is measured in farad. Okay, farad. Okay, just call it F. Okay, so measured in farad. Okay, and also for the inductance, we have that frequency is F. XL is inductive reactance measured in ohms. XL is measured in ohms as well. And then L, okay, L is inductance, and then that is measured in Henry. So you can call it H, Henry. Okay, so I'll quickly write it out again. So we have that XC is 1 over omega C, which is 1 over 2 pi FC, and then we have that XL is 2 pi FL, which is omega L. This is as simple as that. So now you need to note that. So now there's so there are 4 types of electrical circuits that I have shown earlier on. So before I go to the types, I'm going to quickly show you this. Okay, so you have to know this. This diagram actually simplifies everything. This is R. Okay, then we call this is XL, this is XC. Okay, so this simplifies everything. Okay, so now this is resistor. Okay, this is inductive reactance and capacitive reactance. Okay, so let me quickly show you that. Before I go ahead, let me quickly show you the diagram. So for an RL circuit, you can have an RL circuit where you have the resistor and then the inductor connected together. Okay, and then you have something like this AC source. This is an RL circuit. You can have an RC circuit. Okay, so where you have the resistor, okay, and then the capacitor, okay, and then you have them connected together, and then you have something like this, the AC source. Okay, we can have an LC circuit. That's like you have Control Z. That's you have L. You have this, and then